Hi guys, so this video is just a quick run through of a practice quiz similar to the type of quiz that you'll see for quiz 7. So this first question is giving you the energy content of a 12-ounce soft drink in kilocalories, and it's expressed to 3 significant figures, and we can tell that because it's got that decimal point at the end. And this is a lowercase calorie. We're asked to convert this first of all into calories, which is fairly straightforward because we know that that kilo is just a shorthand for writing 10 to the 3. So what we know is that 10 to the 3 lowercase calories is exactly the same as 1 kilocalorie. So what that means for us is that we get 1.50 by 10 to the 5 calories if we drink this 12-ounce soft drink. That's quite a few, isn't it? All right, there we go. Okay, so that's relatively straightforward. We're now asked to convert this into kilojoules, and what we need to think about here is the relationship between joules and calories. And I like to think about this in terms of the specific heat of water. So the specific heat of water is 4.184 joules required to raise the temperature of 1 gram of water 1 degree Celsius. But we also know that the specific heat of water can be expressed in calories like this, and it takes 1 calorie to raise the temperature of 1 gram of water 1 degree Celsius. So what this is really telling us is that 4.184 joules is the same as 1 calorie. And so that's going to be our conversion factor here. So we have 1.50 by 10 to the 5 lowercase calories, and we know that we get 4.184 joules for every 1 calorie, and then finally we know that 1 kilojoule is the same as 10 to the 3 joules. So all of our units cancel out, and there we go, we get our answer. So it ends up being, when we do this, 1.5 by 10 to the 5 times 4.184 times 1 on 10 to the 3. So putting all of that together, and it ends up being 628 kilojoules that we have. And remember, we wanted to go out to 3 significant figures. So there's our answers: 1.5 by 10 to the 5 calories and 628 kilojoules. Okay, let's have a look at the next one now. A chemist carefully measures the amount of heat, and we normally indicate the amount of heat with the unit Q, to raise the temperature of a 736 gram sample, which we normally indicate with a lowercase m, the mass in grams, 736.0 grams. To raise the temperature from -9, so that's my initial temperature, minus 9.9 degrees Celsius, to 4.6 degrees Celsius, so that's my final temperature. Okay. The experiment shows that we needed to do this 1.48 kilojoules, 1.48 by 10 to the 3 joules. What can the chemist report for the specific heat of the substance? Be sure your answer has the correct number of significant digits. Okay, so we know that Q equals m cat, and we know that the delta T is just our T final minus our T initial. And we're trying to solve for the specific heat for the C. So we know that Q divided by M multiplied by T final minus T initial. Now whenever we have multiple things on the bottom line, you always want to get them in parentheses. That's going to be equal to my C. Now we're asked to give the C in specific units of joules per gram per degree Kelvin. And I want to just explain something to you. The change in temperature in degrees Celsius is equal to the change in temperature in Kelvin. And so rather than converting each of these guys here into Kelvin and taking the difference, don't do that. You're just wasting time. It's all going to work out in the end anyway. So just keep that in mind, that the change in temperature in degrees Celsius is exactly the same as the change in temperature in Kelvin, because a Kelvin unit is the same size as a Celsius unit. So let's go ahead and do this and make sure we get the correct units that they wanted. So C is going to be 1.48 by 10 to the 3 joules. The mass, 736.0 grams, multiplied by, and then T final, 4.6, minus 9.9, so plus 9.9. And as I said, that's just going to be, even though we're doing the difference in Celsius, it works out to be exactly the same in Kelvin units. So our units here are looking good. It's going to be joules per gram per degree Kelvin as requested. And it looks like our significant figures here are going to end up being, 4.6 plus 9.9 ends up being 14.5. So that would be 3 sig figs. This number here is 4 sig figs. This number here is 3 sig figs. So it looks like we're going to end up with 3 sig figs. So here we go. 1.48 by 10 to the 3 divided by, put the whole of the bottom line in parentheses, 736 times parentheses 4.6 plus 9.9 parentheses, close the second parentheses, hit enter, and it ended up being 3 sig figs 0.139. 0.139. So most metals have a specific heat less than 1, and it just says of a pure substance, so we don't really know. Okay, so it's not so clear here. All right, looks like we got everything correct there, and that little hint there that the change in temperature in degrees Celsius is exactly the same as the change in temperature in degrees Kelvin, or in Kelvin units, we should say more precisely. So that really speeds things up. Okay, let's have a look at this one. It says calculate the kinetic energy of a 85 milligram raindrop moving at a speed of 2.4 meters per second. Give your answer to 2 significant figures. So the kinetic energy formula is this one. It's half mv squared. There's only a couple of things here. M has to be in kilograms and V has to be in meters per second, or otherwise this formula won't give you the correct units. And the reason for that is because of the way that the joule is defined. 1 joule is equal to 1 kilogram meters squared seconds to the minus 2. So you can see here that we need, our mass has to be in kilograms, and then we're going to do V squared in order to get meters squared second to the minus 2, and V must be meters per second. So when we square that, we get the correct units. All right, so that's it. As long as we do that, we're in business. So let's see if we can do this. 1/2 times by the mass. And so we've got 85 by 10 to the minus 3 grams. and then we need to recognize that that needs to be converted to kilograms, and 1 kilogram is 10 to the 3 grams. So there's our 1/2 times the mass, and then we've got to times that by the velocity squared, so times by 2.4 meters per second, all squared. So there we are, 1/2 times mv squared. So when we do that, we'll get our answer, and I just want to cancel out units. That's going to give me kilograms. Yep, there we go. All right, so 0.5 times, parentheses, 85 by 10 to the minus 3, that's our 85 milligrams, times 1 on 1 by 10 to the 3. And then we're going to times that by 2.4 squared. And I get my answer, and it doesn't look like it's very much. It says it is 2.4, and we're going to do 2 sig figs, 2.4 by 10 to the minus 4, and the units are kilograms, meters squared, seconds to the minus 2 squared, which I pointed out was exactly the same as joules. So not many joules in a raindrop that's moving that slowly, okay, and which is what we would expect. All right, okay, so that's pretty cool. You know, it's only a tiny little raindrop, so it doesn't have a lot of energy. All right, we'll move on to the next one. Next one's kind of fun. It's talking about the interplay between potential energy, energy depending on position, and kinetic energy, which is energy associated with movement. So what we've got here is a bicyclist, and they're stopped at the entrance to a valley, so they have 0 kinetic energy. That's what it means when we say stopped, right? Kinetic energy equals 0. You can call that joules if you want, because they're not moving. They have no energy associated with movement. Now, they're above the lowest point of this valley, so their potential energy is pretty significant. They have some potential energy at this point, all right? And what will happen as they start moving down this valley is that their potential energy will go down because they're getting closer to the bottom of the valley, and their kinetic energy will go up. Sounds really dumb, but they're going to pick up speed as they roll downhill, right? So here he is here. And so where would the cyclist have the highest potential energy? So that's just really code for saying where will they be the highest above the ground. And pretty obviously it's going to be at F. Now, here they are at the moment stopped, right? If they were to roll down the valley and they didn't lose any, any energy due to, air resistance or friction within the bicycle, the highest point they could roll to would be E, because at that point, they'd just be back where they started, right? They'd have the same amount of energy that they began with. But it's a little kind of ambiguous here, but this is definitely where they would have the highest energy. They'd have to pedal a little bit to get up there, right? They would have to pedal from E up to F. So then it says, so that's F for the first one, for the highest potential energy. Where would they have the lowest potential energy? That is when they're like, when they have the least height above the 0 position, and pretty obviously that's going to be D. At that point, they're going to have the lowest potential energy and the maximum kinetic energy, which is good because that's the next question. It says, where would the cyclist have the highest kinetic energy? And so that's going to be D as well. Now, what do we mean by the highest kinetic energy? We mean that they have the highest energy associated with movement. So the kinetic energy is equal to 1/2 mv squared. So the the mass is constant. So wherever the cyclist has the greatest kinetic energy, that's where they're going to have the greatest speed. So that's going to be D as well. So you get 3 Ds there. All right. So then it says, would the cyclist's kinetic energy be greatest at B or D? Well, at D they have like 0 potential energy. They don't go any further. They can't roll any further down here. And they have maximum kinetic energy. At B, they've only turned some of their potential energy into kinetic energy. They still have a little bit, and they have less than the maximum kinetic energy. So the cyclist's kinetic energy would be higher at D, not at B. Okay. Now, you're asked the same question, but it's kind of flipped around. What about the potential energy? Well, at D, the potential energy, as I just pointed out, would be 0. They can't fall any further. At B, though, their potential energy is going to be greater than 0 because they can still roll downhill. So this one is going to be B. Okay, this guy here will be B. Now it asks about the total energy. Well, the total energy is the same the whole way through. We're just converting from potential energy to kinetic energy. To begin with, they have no kinetic energy and they have some potential energy. As we move, what happens is some of the potential energy gets turned into kinetic energy, but the total of the two stays the same because according to the first law of thermodynamics, right, energy cannot be created or destroyed. So at B and D, they have the same total energy. Right? We call the total internal energy. The sum of all of the different types of energy will be the same at both B and D. Okay, so then it says, suppose the cyclist lets off the brakes and coasts down the valley without pedaling. Even if there is no friction or air resistance to slow him down, what is the farthest point the cyclist could reach? And I kind of answered that in the beginning. What's going to happen is we can't end up with more energy than we started with. So what's going to happen is we're going to roll down here. We're going to we begin with 0 kinetic energy and 100% potential energy, and then we roll down, we lose potential energy, gain kinetic energy, and at the bottom we have 100% kinetic energy and 0 potential energy right there. Then we start going up and we slow down. The kinetic energy begins to decrease and the potential energy, because we're rising up above the valley floor, starts to increase. And then we get to E, and at that point we stop once more and we have turned all of our kinetic energy back into potential energy and we stop moving. And so the highest that we can get without pedaling would be E. And I mentioned that in the beginning. At F on this thing, if you want to go from E up to F, you're going to have to pedal a little bit, right? You're not going to get there just by rolling. Now, in this world where there's no air resistance and there's no friction, the cyclist would actually just kind of like roll backwards and forwards between A and E indefinitely, right? They would just be stuck in that valley and they would just keep moving backwards and forwards. It would be kind of fun. All right, now that doesn't of course happen because frictionless, air resistant-less systems don't exist. We'd have a perpetual motion machine if that was the case. All right, here's another one where we have to calculate kinetic energy. The key things here is make sure you get your units correct and make sure you get your sig figs correct. So we know that kinetic energy equals 1/2 mv squared. M has to be in kilograms, which is convenient because in this case they gave it to you in kilograms, and velocity has to be in meters per second, which again they gave it to in this case. So the only thing we've got to decide here, the only thing we've got to do here is round correctly to 2 significant figures. So this is a baseball. It weighs 0.16 kilograms, which is definitely more than the raindrop weighed. So we're expecting it to have greater kinetic energy than what we got previously. So the kinetic energy equals 1/2 times 0.16 kilograms times by 43.0 meters per second, and then that has to be all squared. So we got that. Let's see what we get here. 0.5 times 0.16 times 43 squared. Nice and easy, right? So that ends up being 100, and we want this out to 2 sig figs, 150 kilograms meters squared per second squared. And that's the same as 150 joules. And you're like, well, that was too easy. But when you look at the units here, it wants it in kilojoules. So we've got to do one step further. 150 joules times, and 1 kilojoule is the same as 10 to the 3 joules. So that ends up being 0.15 kilojoules. So we need this in these units, we need this expressed to 2 significant figures. So all the way through here, I've just used 2 significant figures because that's what the answer was asking for. So 0.15 kilojoules or 150 joules, which is considerably more than the raindrop, which was like 10 to the minus, I think it was 10 to the minus 4 joules. So, you know, it was 2.4 by 10 to the minus 4 joules. Obviously, a baseball that is being picked pretty darn hard, 20 times faster than the raindrop was moving, has a lot more kinetic energy. So it's heavier and it's moving quicker. All right, let's have a look at this one. Looking like a unit conversion problem, isn't it, right? It says complete the following table. Be sure each of your answer entries has the correct number of significant figures, and it's 3 of those problems concerning the energy content of food. So what have we got here? We have to convert between calories, kilocalories, and kilojoules. So we've just got to remind ourselves of how these things are related. We know that K equals 10 to the 3 or times 10 to the 3, and we know that 1 lowercase calorie is the same as 4.184 joules. So as long as we keep those things in mind, this should be relatively straightforward. And then we've just got to keep an eye on our sig figs. And it looks like in this case, everything is going to get rounded to 3 significant figures. So let's do the first row. We have to turn some calories into kilocalories and kilojoules. It's probably also worth noting that 1 kilocalorie is the same as 4.184 kilojoules. So we can kind of do a little shortcut if we want here. So 4.50 by 10 to the 4 calories times, and we're going to go to kilocalories. 1 kilocalorie is the same as 10 to the 3 calories. So that's going to be drop us down to 45.0 kilocalories. And you're just going to divide by 1,000, all right? And we're keeping that as 3 sig figs. I've got a tendency to write an uppercase C for calories, that we should be aware that it has a lowercase c in this case. All right, so that's the first part of the problem, and now we're just going to use our next conversion factor, and we know that we get 4.184 kilojoules for every 1 kilocalorie. There we go. So you just got to times that by 4.184. So 45 times 4.184 gives me 188 kilojoules. 188 kilojoules. Okay, so we got the first one done. Not bad. So we've got 45 kilocalories and a 45.0 and 188. All right, let's go on and do the next one. Same conversion factors are going to be used. We use the same procedure. This time we're starting with kilocalories. So we may do a slightly different approach. So for B, 75.0 kilocalories and 1 calorie there. 10 to the 3 calories is the same as 1 kilocalorie. So what this means is that we've got 7.50 times 10 to the 4 calories. There we go. All right, 3 significant figures. That looks good. And then I'm going to do my second conversion here. I'm actually going to do it just separately. 75.0 kilocalories times, and we know that we get 4.184 kilojoules for every 1 kilocalorie. So that's nice and easy. 75 times 4.184. We want 3 significant figures, so it ends up being 314 kilojoules. We can check all of our units. Yeah, our units are good in both cases. So there's our next one, 7.4 by 10 to the 7.5 by 10 to the 4, and then this one 314. Okay, so then finally we're going to turn 1,000 kilojoules, which is quite a lot of food, into kilocalories and calories, and I'm going to do it like this. So 1 by 10 to the 3 kilojoules. I'm going to go into kilocalories because that's nice and easy, and 1 kilocalorie is the same as 4.184 kilojoules. There we go. So they cancel like so. So that will give me 1 by 10 to the 3 divide 4.184. That gives me 239 kilocalories. There we go. Okay, and then now we're going to turn, so that's one of our answers. Now we're going to turn that into calories, and we know that we get 10 to the 3 calories for every 1 kilocalorie. So that ends up being 2.39 by 10 to the 5 calories. We'll just check all of our units here. That looks good. Yep, everything looks good. All right, cool. So writing those in, I don't know if I can be bothered, but we'll do it. 2.39 by 10 to the 5 for that guy, and then 239 kilocalories. Okay, so not too bad, just converting between different units of energy. It's pretty straightforward. We've been doing conversion factors for a really long time now. All right, there's got to be something a little trickier coming up, and this looks like it. All right, this looks like a fairly decent story problem. Let's see what we've got here. It says a chemical reaction takes place inside a flask submerged in a water bath. The water bath contains 4 kilograms of water. So this is your mass, right? 4.00 by 10 to the 3 grams. At a temperature of 24.8 degrees Celsius. So this is your initial temperature. There we go. During the reaction, 91.9 kilojoules of heat flows out of the flask and into the bath. So Q equals 91.9 by 10 to the 3 joules. Then it says calculate the new temperature of the water bath. So we want to calculate the final temperature like so. It says you can assume the specific heat capacity of the water under these conditions is 4.18 joules per gram per degree Kelvin. Now, so what that means is that C is 4.18 joules per gram, and remember per degree Kelvin is, or per Kelvin unit is the same as per degrees Celsius. So this doesn't look too horrible, right? We know that Q is equal to mc delta T, and we also know that delta T is equal to T final minus T initial. So Q would be equal to mc multiplied by T final minus T initial. So we can reorganize and solve for delta T here, right? So Q on MC equals delta T. So we have 91.9 by 10 to the 3 joules divided by, and whenever you've got multiple terms on the bottom line, you always want to, or even in the top line, you always want to make sure they're in parentheses. 4 by 10 to the 3 joules times by 4.18 joules per gram per Kelvin unit. So joules and joules will cancel out, and sorry, that was grams. Grams and grams will cancel out, joules and joules will cancel out. And that'll leave us with 1 over Kelvin, which is just Kelvin. So delta T in this case ends up being 5.496, and we'll round to the correct number sig fix in a moment, Kelvin units. And we know that a change in Kelvin units in the temperature is exactly the same as the change in Celsius units. So those things will be equal. So our temperature is going to change by 5.496 degrees Celsius. So delta T equals our T final minus our T initial, or we can reorganize this and say that T final is just equal to our delta T plus our T initial. So that's it, isn't it, right? So our initial temperature was, I believe, 24.8. Let's double check that, 24.8. And then our delta T was 5.496. So if we add those two together, our T final ends up being, it's going to be it's at 30.3 degrees Celsius. So it goes up by about 5 degrees. So our reaction is exothermic. It releases some heat. Okay, so a lot of unit conversions in here, a lot of understanding the distinction between kinetic energy and potential energy, and then just a couple of problems where we're using the Q equals MC delta T relationship. Okay, I hope you found that helpful, and good luck on the upcoming quiz.